Welcome back to my kitchen, where we're going to begin our coverage of carbohydrates. Very fittingly, I have just recently purchased this absolutely gargantuan sweet potato. I'm going to be making sweet potato latkes in the effort to maybe begin a little bit of glycogen supercompensation for an upcoming triathlon. That's the sexy-minded term for carb loading, and perhaps we most associate carbohydrates with their ability to serve as an energy source or as energy storage molecules. However, carbohydrates have a broad range of different activities and different things in the cellular system that they are so important for, ranging all the way from things like being components of ATP. Remember that in UDP glucose, we see that ribose is an important sugar in those molecules, in that molecule of life, DNA and RNA, deoxyribonucleic acid. So we recognize those as being important roles. But additionally, we know that carbohydrates play roles in signaling. They play structural roles. Additionally, sometimes they play a functional role in making cells just a little bit slippery. For example, your red blood cells are actually coated with carbohydrates that allow them to slip through capillaries, and bacteria cells are sometimes coated in a carbohydrate layer that allows them to slip out of the grasp of a phagocytic white blood cell, therefore allowing them to have high defense against your immune system. So these are just a few of the roles, the many roles that carbohydrates play within our body. And let's go ahead and jump right in and talk a little bit more. And of course, in this particular sweet potato, the glucose molecule that you can see I have on my shirt here, sweet, of course, is very complex, meaning that it's a polymer of many, many different monosaccharides or sugars all linked to one another, so making it much more complex. This on my shirt is a simple sugar, and actually that's where we're going to begin our coverage. Let's begin with the smallest unit of carbohydrate structure called the monosaccharide. Mono meaning one, saccharide meaning sugar. Monosaccharides are simple sugars, and they have the general molecular formula of CH2O. N will have to be greater than or equal to 3. So if we go ahead and write the ratio for this molecular formula, it is 1 carbon to 2 hydrogens to 1 oxygen. That is to say that there are double the number of hydrogens than either oxygens or carbons. We can have our polyhydroxyaldehydes, also and more frequently termed the aldoses. And the aldoses are characterized by an aldehyde, you guessed it, an aldehyde functional group. So an aldehyde functional group is what's going to typify the polyhydroxyaldehydes, or more commonly called the aldoses. And we can get different sized aldoses. For example, we might have aldoses that have 3 carbons, and we would call those aldotrioses. We can then likewise get 4 carbon aldoses called aldotetroses, 5 carbon aldopentoses, and probably even before I say it, you have already written down the aldohexoses. We likewise can see another form of monosaccharide called the ketoses, or the polyhydroxyketones. Remember that these are going to have a different functional group. So they're going to have the C double bond O. That'll be the same, but then to either side is a carbon. The ketone functional group is going to typify the ketoses and contrast them with the aldoses. So they contain multiple hydroxyl groups and a ketone functional group, that being the key difference between those and the aldoses. Likewise, we can get the ketotrioses, ketotetroses, ketopentoses, and ketohexoses. The simple autotriose is a molecule of which you have probably heard, glyceraldehyde. On the left-hand side, we see the image of glyceraldehyde and recognize that it has that aldehyde functional group. We also recognize the multiple hydroxyls typifying this particular aldotriose. Now notice that this is drawn as the Fisher projection, so we recognize that the horizontal bonds are coming towards you and out of the page, whereas the vertical bonds are going back and away from you. I decided we should like develop a yoga pose for a Fisher projection, but that's how those are indicating the overall structure. We'll notice that with numbering within the aldehydes, we can actually see that the first carbon, carbon number 1, is always the aldehydic carbon. So this is carbon number 1, carbon 2, and carbon number 3. Notice, and some of you might already be recognizing that lovely Barbie pink star on the central carbon, and recognizing that that is there because this is a chiral carbon center. That is, it is bound to, this carbon is bound to 4 different substituent groups, making it chiral. Now, you might be thinking, gosh, you know, I have trouble recognizing that. What's another way that I could know that this particular aldotriose has a chiral carbon center? Well, if you want to use a quantitative method, you can note that the number of chiral carbon centers is always equal to C minus 2. Now, this is only true of the aldoses, so bear that in mind. But if you take C minus 2, you'll get the number of chiral carbon centers. And sure enough, here the number of carbons is 3 minus 2 means that there is in fact 1 chiral carbon center. So what that also means, many of you will be recalling your chemistry, is that there are 2 different stereoisomers for glyceraldehyde. We've noted the D-glyceraldehyde here on the left-hand side, and you might recall that that quite literally means that when this molecule is hit with plain polarized light, it rotates it in a dextrorotatory way. That contrasts with the other stereoisomer of L-glyceraldehyde, which will rotate plain polarized light in a levorotatory way. Let's go ahead and draw L-glyceraldehyde, recognizing this as a mirror plane and drawing the mirror image over here for L-glyceraldehyde. And just noting that this is the other stereoisomer. And of course, the stereochemistry occurring around that central chiral carbon center. So D and L-glyceraldehyde. You might recall from the world of amino acids that the L stereoisomers are the more common. This is not true in the world of carbohydrates. Instead, the D stereoisomers tend to be the more common of the 2. Let's go ahead and move from the aldotrioses up to the aldotetroses, looking at what occurs as we add another chiral carbon center. So let's look at the next category, longer chain aldoses, in which we add another chiral carbon center. That is to say, if you picture another carbon bound to its hydroxyl being inserted between the carbonyl carbon 1 here and the primary alcohol, that is to say what was our carbon number 2, we've now inserted another H bond C bond OH group there. Now, what is really interesting is as we go from the small aldotrioses that could easily be labeled levorotatory or dextrorotatory, when we get to larger aldotetroses, pentoses, hexoses, we go by history and tradition rather than whether it actually rotates plain polarized light. So what we base it on is actually looking at the last chiral carbon center. So whichever is the most highly numbered chiral carbon center, if its hydroxyl is to the right in a Fisher projection, then we would say that it is dextrorotatory. So important to keep in mind that that is the way that we consider the larger aldoses. So here we recognize that we have our numbered carbons 1 through 4. If we use our formula for figuring the number of chiral carbon centers and recalling it to be the number of carbons minus 2, then we can recognize that this would have 4 minus 2 or 2 chiral carbon centers, and we can see them here are 2 different chiral carbon centers. That is going to mean that we're going to have more stereoisomers for the aldotetroses than we did for the aldotrioses. And in fact, in answering this question, how many stereoisomers are possible for the aldotetroses, we have a simple formula where the number of stereoisomers is always going to be equal to 2 raised to the n, where n is equal to the number of chiral carbon centers. So in this particular case, we know that the number of stereoisomers is going to be 2 raised to the 2 or 4 stereoisomers that we could draw. We'll turn our attention now to the ketoses, and as expected, we see that ketone functional group even in the simplest keto trios, and this simple keto trios is called dihydroxyacetone. Dihydroxyacetone is a molecule that perhaps you already recognize, but let's draw our attention to the fact that it does have that simple ketone group, so C double bond O, bond R, bond R, and we recognize this as being the 3-carbon ketone. But maybe the thing that we fail to see, because it is just simply not there, is a chiral carbon center. In fact, the dihydroxyacetone thus is the only stereoisomer for the keto trios. That is to say that when we think about the stereoisomers for the ketoses, rather than calculating the number of chiral carbon centers the way that we did for the aldoses by taking the number of carbons minus 2, we now for the ketoses have a new rule, and that is that we have to take the number of carbons minus 3, and that gives us the number of chiral carbon centers. Notice that in this particular case, C minus 3 is 3 minus 3, and it's 0. So we don't have a single chiral carbon center, and this is the only keto trios. But not to worry, for those of you who are in love with the rotation of plane polarized lights, I can totally understand that. It's a pretty sexy phenomenon. Don't worry, because as we move up from the keto trioses to the keto tetroses, we will see the insertion of a chiral carbon center. We'll go ahead and look at the keto tetroses and keto pentoses. I'm going to go ahead and draw one. This is the keto tetros called D-erythrulose. Now you might think, wow, that sounds pretty familiar. D-erythrose is an aldose, but notice that ketoses, in these longer chain ketoses, we just insert the UL here. So this UL indicates that we're looking at a ketose. And of course, here's D-erythrulose. We could just put that mirror image plane and go ahead and draw L-erythrulose. And of course, using our rules there for finding the stereocenters, we know that we can simply take C minus 3, where we will have one chiral carbon center, and then in order to know the number of stereoisomers, that's simple, 2 to the 1, which means we, of course, have 2 stereoisomers. As you've pondered the drawings of glucose that we've been making, you may have thought, wait a minute, I thought I knew what glucose looked like. And it might be that what you were picturing was the cyclized version of that particular aldose rather than the linear chain version. We are going to show that cyclization process, and let's begin by drawing our linear chain anomer of glucose. Course, recalling that it's carbon number 3 that is a little bit different, the unique one, where the OH is on the left side in the Fisher projection. We can number those carbons. And then let's consider what happens when this cyclizes, and recognize that in the formation of a 6-membered ring, which we may have come to know and love glucose as forming, we can get a nucleophilic attack on the carbonyl carbon of the aldehyde, so the aldehyde carbon, and that nucleophilic attack can happen in one of 2 ways, and it can therefore lead to the generation of 2 different anomers. So in equilibrium with the linear chain form of glucose, we can get the alpha form. So recognize that when this oxygen here does the attacking, that means that it's going to become a member of the ring. So here is our oxygen of carbon number 5. It becomes a member of the ring. And this forms a 6-membered ring in which when we when we attack one direction, the OH will go below the plane of the ring in what we call the Haworth projection. So remember that this is, of course, our Fisher projection. And these are our Haworth projections. And so this form, then carbon 1 has the OH on the bottom of the ring, and then we just trace the Fisher projection from there. So this is carbon 1 in our Haworth projection. Here's carbon 2. And in the Fisher projection, if the hydroxyl is on the right-hand side of the plane of the ring, then it goes below the plane of the ring in the Haworth projection. So there's our odd man out there. The hydroxyl on carbon 3 is above the plane of the ring and then below the plane of the ring. And then notice this, poor carbon number 6 got left out of the ring altogether. It wasn't a part of the cyclization. So CH2OH, carbon 6 outside the plane of the ring. But remember that the nucleophilic attack could occur in one of 2 different ways, giving rise to 2 different anomers. And we should go ahead and draw the beta anomer, because as it turns out, generally the beta anomer is, while they're all 3 in equilibrium with one another, the beta anomer tends to predominate. And so our hydroxyl in the beta anomer is above the plane of the ring, and that's what differentiates it. Everything else, of course, is exactly identical to the alpha anomer, carbon 6 still outside the plane of the ring, and we can number our carbons. And recognize that there is an interconversion, an equilibrium between these alpha and beta forms. So let's go ahead and give these a name. This is alpha D-gluco. You would think it would just be alpha D-glucose, but in order to represent the ring, we call it alpha D-glucopyranose. Pyranose six-membered ring. And then this is beta D glucopyranose. And what's kind of cool about this is that with this cyclization, if we remember back to the number of chiral carbons in the Fischer projection, we recall that that number of chiral carbons was 1, 2, 3, 4 chiral carbons, or we could take the 6 minus 2. But when we cyclize, it introduced a fifth chiral carbon center, and this is a very famous chiral carbon center. It's termed the anomeric carbon, and the anomeric carbon, we'll label it here. We'll find out later is the reactive carbon in any long polysaccharide chain. So a very special carbon indeed. So you also could note it is the most highly oxidized carbon in the glucopyranose molecules. So I mentioned that the beta anomer predominates, usually about 64% beta at around 31 degrees and in kind of a physiological conditions, but there is certainly mutarotation. So I'm going to jot that term down. Maybe it's one mutarotation, which is the interconversion between all three different anomers, usually less than about 1% linear form. So if we draw our attention to the anomeric carbon and just kind of I'm just going to make a dotted circle right around this anomeric carbon. This chemical group is called a hemiacetal. So in this case, C bond OH, bond H, bond O, so here go to bond O, bond R, and then we call this R prime. So this is a hemiacetal, and certainly we've got the same thing going in our alpha D glucopyranose as well, is also a hemiacetal. It's just that we recognize the minor distinction there. It's still a hemiacetal. Now, of course, in a ketal, when a ketone cyclizes, we get the formation of a hemiketal instead. And if I tell you that we want to go ahead and draw alpha D fructopyranose, well, we know that pyranose means six-membered ring. If it said furanose, that would be a five-membered ring. So we know we want to get a six-membered ring. We know that the nucleophilic attack will occur on the carbonyl carbon of the ketone. And so in order to get a six-membered ring, that means that we recognize that this is going to be the first position of the ring, right? Carbon 2 will be the first position of the ring. So 1, 2, 3, 4, 5, 6. The nucleophilic attack is going to have to come from the hydroxyl on the carbon number 6. So in order to get a pyranose ring, we could also get a furanose ring where the hydroxyl on carbon 5 would do the attack. So again, drawing our equilibrium here, we can recognize then we've got a six-membered ring where the oxygen on carbon 2 is a member of the ring. But of course in this case, hey, look who's left out. Carbon 1 is left out. The hydroxyl still goes below the plane of the ring because we're looking at the alpha anomer. So got the OH there. So carbon 1, 2 now accounted for. Carbon 3, remember the OH is on the left of the Fisher projection, so it goes above the plane of the ring, and then below for carbon 4, it's on the right of the Fisher projection, so it goes below. And then continuing on, carbon 5 below. And then, hey, check it out. The 6th position of the ring is just got 2 hydrogens on it. So looks like we have successfully drawn alpha D frugidopyranose. But I also want to draw your attention to the fact that now at the anomeric carbon, we have a hemiketal. So this here, right, if we're kind of looking at this is going to be a C bond OR once again, bond R prime once again, bond OH once again, but check it out, R double prime.